Bismillahirrahmanirrahim. Assalamualaikum. How are you guys? This is your sweet friend Mansoor Ahmad with Overt Chemistry channel. I hope that all are going well. So as you know, we have started the electrophilic aromatic substitution reaction of the benzene. So today we will discuss the first example of aromatic substitution reaction of the benzene, which is halogenation. So today's topic is about halogenation of the benzene. Now what does mean by the word halogenation? Here the term halogenation means the addition of halogen. So today basically we add the electrophile, which is halogen, which belongs to halogen family. So this process in which we add an halogen atom to the benzene molecule, and which one of the hydrogen atom of the benzene is replaced, this process is known as halogenation. So here the word halogenation means addition of halogen. Addition of halogen atom. We basically add an halogen atom to the benzene ring. So this is our first example. Now we will discuss the first example of halogenation of the benzene. So first I will write its general definition. After that I will explain its general reaction. After the general reaction I will explain its specific example. Like that how this process occurs in the members of halogen family, I mean in all members. Understand? After that I will explain the mechanism of one reaction. Almost the mechanism of all electrophilic aromatic substitution reaction is almost equal to each other with some exceptions. Understand? So first I will explain the definition of halogenation. What is the definition of halogenation? It is very easy. Suppose this is a benzene molecule. This is what? This is a benzene molecule. This is one of the hydrogen atom of benzene molecule. With this benzene molecule I am reacting specially halogen molecules. This is X2. X2 is simple halogen molecule. Now what happens? Basically this hydrogen atom of the benzene will replace by the help of this X atom. This is halogen atom. Understand? This process is known as halogenation. Halogenation is the process in which one hydrogen atom of the benzene ring is replaced by the help of halogen atom. This reaction is carried out in the presence of a catalyst, which is anhydrous Lewis acid. We use the catalyst in this reaction, and the reaction is carried out in darkness. What would be the condition for temperature for these reactions? We do not use we do not employ the temperature to this reaction. The reaction is generally carried out at room temperature. So first I will write the definition of halogenation. So the definition is very easy. The definition of halogenation is the replacement of hydrogen atom, the replacement of hydrogen atom, the replacement of hydrogen atom, this hydrogen atom of benzene ring by halogen atom. This X is our halogen atom. Understand, everyone? By halogen atom in the presence of anhydrous Lewis acid. Understand, everyone? Anhydrous Lewis acid using as a catalyst. Anhydrous Lewis acid will be our catalyst in this reaction. At room temperature will be RT, that is room temperature. At room temperature to form, what will be the final product formed during the process of halogenation? That is halobenzene, which we will explain. To form halobenzene, is known as halogenation of benzene. Halogenation of benzene. This is the general definition of halogenation of benzene. Basically, in this process, the hydrogen atom is replaced by the help of halogen atom. We will use a catalyst, that is anhydrous Lewis acid. The temperature will be carried out at room temperature, and the final product will be halobenzene. This is the main definition related to halogenation of the benzene. Understand? If I write its general example, then it will be more useful for us. Suppose I am writing a general example of halogenation of benzene. Suppose again this is a benzene molecule. This is one of the hydrogen atom of the benzene molecule. With this benzene molecule, I am reacting X2. What does mean by X2? X basically represent the halogen family. Halogen family, which means this is 7th A group of periodic table, which contains chlorine, bromine, iodine. But astatine is also the member of halogen family. I am not showing that here because it is an radioactive element. Now what happened? This is halogen molecules. This X may be with us fluorine atom, chlorine, bromine, iodine. But in case of halogenation, we study just these two, that is chlorine and bromine. I will discuss the reason that why rest of the two are not used during these reactions. Understand? So this is halogen, which is basically our halogenating agent. Now what does mean by halogenating agent? Halogenating agent means the agent which provide X atom. Understand? So here we are taking specially halogen molecules, that is X2, suppose Cl2, Br2, I2. These are called halogenating agents, which are our halogen molecules. Understand? And this reaction is especially carried in the presence of anhydrous Lewis acid. Anhydrous Lewis acid. What does mean by anhydrous Lewis acid? N means without, hydrous means water. That means we have to use a Lewis acid which is without water, which doesn't contain water molecule. Why it is a condition for Lewis acid to be anhydrous? I will explain it in the mechanism. There are two important questions. Question number one, that why we are using Lewis acid in these reactions? Number one. Number two, why we are using anhydrous Lewis acid in this reaction? These two important questions I will explain in the mechanism. Understand, everyone? Now, this Lewis acid that we can use in these reactions, as I told in my previous lecture too, that's almost with us ferric halides. Ferric halides are what? These are Lewis acid. What is the general representation? F FeX3. These are ferric halides. Similarly, we can also use aluminium halides. Aluminium halides. These are also the examples of Lewis acids. The general representation of aluminum halide is AlX3. Suppose FeX3, that is ferric chloride, FeCl3. This can be used as a Lewis acid. Similarly, FeBr3. This can also be used as a Lewis acid. In case of aluminum halides, we can use AlCl3, aluminum trichloride, as a Lewis acid. Similarly, AlBr3, this can also be used as a Lewis acid. So these are what? These are basically the examples of the Lewis acids which are used during these reactions. Understand? These are what is not? These are Lewis acids, and that should be an address. Especially this reaction is carried out in the presence of darkness. Darkness. The temperature is RT. RT means room temperature. There is no requirement of temperature for this reaction, I am telling again, and the reaction is carried out in the presence of darkness. Now, why this reaction is carried in the presence of darkness? If I use ultraviolet light, or if I use high temperature, then what would happen to this reaction? Different. If I use ultraviolet light plus ultraviolet radiation plus I use high temperature, then there will be addition reaction rather than substitution reactions. Understand? There, in case of high temperature and ultraviolet radiation, our product will be addition product. Understand? While in case of darkness and RT, our reaction will be substitution reaction and the product will be substituted product. Since benzene wants to go through substitution reactions rather than addition reactions, therefore these two are the requirement for the substitution reaction of benzene. Understand? So we use darkness plus RT in this reaction. Now what happens if I apply these conditions to these two, that means benzene and halogenating agent? Then nothing, simply this X atom will react with this hydrogen atom of the benzene molecule. Now one quantity here formed will be HX. Understand? This is known as halogen acid. Halogen acid. HX is different. What? This is halogen acid, and this X atom will attack on this benzene molecule because here one of the hydrogen atom leaves, leaves its place. That's why the X atom will occupies the position of hydrogen atom. That will be simply a substitution reaction will take place. So this is basically what? This is substitution reactions in which the hydrogen atom of the benzene is replaced by the help of this X atom. So what will be our final product? Our final product will be a benzene molecule with X atom. Benzene molecule with X atom, which is known as halobenzene. This is what is want. This is halobenzene. This is the general reaction of halogenation of the benzene. Again, I am telling, I have written just the general example. This X atom may be with us in case of halogenation, chlorine and bromine. Even in some cases, we also studied the iodine. Now note its general definition with its general example. I will explain the specific example now, especially about the halogenation of benzene. So note this one doesn't. So now this is the general examples with the specific examples. The first one is the general example in which the benzene is reacted with halogen. that is X, in the presence of anhydrous Lewis acid at RT, what is formed? Allobenzene plus halogen acid. Now, if I use chlorine molecule in X atom as that if chlorine is used as a halogenating agent, then what happens? For example, here I am using Cl2 instead of these two X atom. I am using these two chlorine atoms. Now what happens? If I use a chlorine atom here, so there must be a Lewis acid which contains chlorine atoms. Like for example, here I am using aluminum trichloride. Understand here, what? If here comes chlorine, then you have to use here also a chlorine containing Lewis acid. If here is a bromine just like this, so there should be a bromine containing Lewis acid. Understand that? Now what happened? If I use Cl2, then the process is known as chlorination. Then we give a special or particular name to that reaction, to that halogenation, which is named specially after the halogenating used in the reactions. Suppose here is chlorine is halogenating agent, Cl2, that is chlorine molecule, so the process is known as chlorination. What will be the product formed during the chlorination? That is chlorobenzene. Since X represents Halo, now X is chlorine, therefore instead of halobenzene, the product becomes chlorobenzene, because chlorine is attached with the benzene molecule. With the chlorobenzene, another product, that is halogen acid. Understand? X again represent here halogen. If there is chlorine atom with hydrogen atom, then the particular name of halogen acid is hydrochloric acid. Understand? In case of chlorination, what is our electrophile? Especially Cl+, that is chloronium ion, is electrophile during the process of chlorination. So when positive charge comes on the chlorine atom, it is known as chloronium ion. Just whenever a positive charge comes on the halogen, it is known as halonium. Now, as halogen in this case is chlorine atom and there is a positive charge of chlorine atom, therefore it is known as chlorinium ion, which is the electrophile during the reaction of chlorination. Understand that? Now, if I use bromine Br2 as a halogenating agent, so what will be the process? The process will be simply bromination. Bromination is what? Bromination is a process in which one of the hydrogen atom is replaced by the help of bromine atom. Especially not bromine atom, but brominium ion will replace this hydrogen atom. Because brominium ion, here again a positive charge comes on bromine, that's why it is known as brominium ion. As I told that name is always used for positive charge. Since there is positive charge or bromine, that's why it is known as brominium ion. This is our electrophile in case of bromination. What is the product formed during the bromination? That is bromobenzene, because the bromine is directly attached with the benzene molecule. Along with bromobenzene, there is HBr is also formed as a side product, which is known as hydrobromic acid. So here HBr, hydrobromic acid, is what? This is halogen acid. Understand this one? This is very easy. Now, if I use iodine as a halogenating agent, then the process is known as iodination, which is different from rest these two, that is bromination and chlorination. Understand this one? The process of iodination is different from these two. I will explain the reason that why these two are different from the iodination. Understand? Suppose if I write just the reaction like I wrote in these two. Suppose this is the reaction. I have taken a benzene molecule. With benzene molecule, I have reacted to iodine molecule. And I have used a catalyst, that is Lewis acid. Understand? If I react iodine molecule with benzene molecule in the presence of Lewis acid, then no doubt iodobenzene will form as a product along with iodobenzene HI, that is hydroiodic acid, that will also formed as a side product during this reaction. Now what happens? Especially this is a reversible reaction. Iodination is a reversible process. These are not processable process, these two processes, but iodination is a reversible process. Now question arises that why it is a reversible process, and what is the story, what is the reason behind this that make the process of iodination as a reversible. Look at this, dear student. When hydroiodic acid is formed with iodobenzene, now this HI, which is hydroiodic acid, is basically a strong reducing agent. This is a very strong reducing agent. As it forms during the reactions, immediately this strong reducing agent reduces the iodobenzene, which in turn form the simple benzene molecule. So as our desire was to form the iodobenzene, as iodobenzene forms in the reaction, but along with the formation of iodobenzene, as HI is also formed, which is a strong reducing agent, the same strong reducing agent again reduces this iodobenzene to form what? Simple benzene molecule. That means our product, our desired material, our desired product, that is iodobenzene, is totally destroyed. We are unable to get that product by using this kind of method for the iodination. Now what happened? What we should do to stop this reverse process back? What we should do? There is a method to stop these reactions, to stop the simple benzene molecule back from the iodobenzene. So what we should do? Basically, we have to alter the procedure of forming the iodobenzene. How we can do it? Basically, in case of iodination, we have to use a strong oxidizing agent. Understand what we use? We have to use strong oxidizing agent in case of iodination. Why? As I told, the reason that if we do not use a strong oxidizing agent, this product will be converted to this one. So our desired product will be totally destroyed. Now, if I use a strong oxidizing agent, understand that oxidizing agent, if I use in acidic medium, for example, I am using here sulfuric acid as a acidic medium, then what happens? Then simply iodobenzene will form. Understand, student? Now you have to keep in your mind, in case of Lewis acid, along with the iodobenzene, HI will also form, while in case of strong oxidizing agent, there will be no HI. You have to keep this in your mind. Only there will be iodobenzene as a product. Understand? You have so generally the oxidizing agent that we use in case of iodination is periodic acid, or we can also use hydrogen peroxide for the process of iodination. So what is the work, or what is the job an oxidizing agent used during the process of iodination? Basically, the oxidizing agent converts this iodine molecule into just iodinium ion. Just these convert oxidizing agent this to I plus. I plus is what? This is called iodinium ion, which is our electrophile. Now there is a very clear reason, there is a very big story behind this, that what is the that if we use oxidizing agent that form I plus, then what happens? Why we use this? This is a separate topic. If I explain it here, it becomes more lengthy. The lecture will be more lengthy that's why I cannot explain this. Inshallah, I will make another separate video on related to the iodination. So understand these points. I hope that you have understand well all of these points, and we will explain now rate of the halogenation. That what is the rate of halogenation in case of halogenation, what is the order. So we have to remember that the rate of halogenation is basically, since as I told that basically the halogen family contains these atom, X atom, basically halogen contains fluorine, chlorine, bromine, iodine. Statine is radioactive, therefore I am not showing it here. So now in case of these four, which will be what will be the rate of halogenation? Understand it? In case of these four, the rate of fluorine, I mean if I use fluorine as a halogenating agent, the process will be fluorination. The rate of fluorination will be most of the higher in case of the halogen atoms, halogen family. So higher will be the rate of the halogenation in case of fluorination. After that will be chlorination. After chlorination there will be bromination, and the last one will be iodination. It means that fluorination is highly fast process, and on the other end iodination is very slow process. Understand? Now why halogenation is the fastest among these one? The reason is that since fluorine is a very strong electronegative atom or element in the periodic table, the electrophile formed of this fluorine is highly unstable, highly reactive. Therefore the rate of the reaction will be also faster as compared to rest of these. On the other end, why the process of iodination is very slow? Because the electrophile formed during the iodination, that was iodinium ion, is very not that much reactive as fluorine. That's why its electrophile is not too much reactive. The reaction becomes what? Slower as compared to rest of these. So what we happen, basically we take just these two, that is chlorine and bromine. I mean in case of halogenation, we specially are in almost we study just chlorination and bromination, because the process of fluorination is very fast and explosive. On the other end, the process of iodination is very slow, which requires much time for the completion of the reaction. Understand, everyone? Now I will explain the mechanism of the chlorination. I will explain the mechanism of chlorination. You note it? Now I will explain the mechanism of chlorination. Now we will discuss about the mechanism of chlorination. So the mechanism is basically consists of 3 steps. We will discuss it. Step number 1. Step number 1, which is known as generation of electrophile. Generation of electrophile. Just remember that in electrophilic aromatic substitution reaction, always our first step will be the generation of an electrophile. Why do we generate an electrophile in first step? Because this is electrophilic substitution reactions. In electrophilic substitution reactions, the initial attack is always done by an electrophiles. Understand? Now, to generate an electrophile, we generally use Lewis acid. Now, I will explain those 2 questions which I asked in the start. Question number 1, that's why we use Lewis acid in these types of reactions. To answer this question, listen the reason different. We use Lewis acid in this type of reaction because Lewis acid help us in the formation of an electrophiles. How the Lewis acid help us in the generation of electrophile, we will discuss. Since we know that Lewis acid is basically electron pair acceptors. Understand what is the definition of Lewis acid? those species are those compound which accommodates the lone pair of electrons. Why Lewis acid accommodates the lone pair of electrons? Because they possess vacant orbitals. Now we will explain the detailed reason. How we explain the Lewis acid? Why we are taking? I will tell the reason now. Suppose this is a chlorine molecule. Understand? We know that each of the chlorine atom possesses 3 lone pairs of the electrons. These are the lone pair of electrons. With this chlorine, I am taking a Lewis acid, that is almost AlCl3 in this reaction. Aluminum trichloride is Lewis acid as I am using, and that should be in address. I will tell the reason. Understand? We know that Lewis acid has an vacant orbitals. This is what doesn't. This box represents the vacant orbital that is present with Lewis acid. Now I will tell that how this vacant orbital is present with this Lewis acid. I am telling here. Suppose we know that aluminum is an atom in the periodic table whose atomic number is 13. Understand? Now if I write the electronic configuration of aluminum, 1s2, 2s2, 2p6, 3s2, understand, student? 3p1. This is the electronic configuration of aluminum. If I write it in blocks, this is 1s, student. This is 2s. Both of these are filled. Now this is partial. This is partial. This is second. Since we know that P has 3 more subatomic orbitals, that is 2px, 2py, 2pz. Understand? There are 2 electrons in each of the subatomic orbitals. And this is 3s2. Again, there are 2 electrons in 3s2. And 3p6, there are again 3 subatomic orbitals in 3p, 3px, 3py, 3pz. There is only 1 electron in the p. Now this is the electronic configuration of aluminum in growth state, not excited state. In especially excited state, this 1 electron present in 3s2 will jump to 3py according to the rules of electronic configuration, because there is vacant subatomic orbitals available. So when the electron jumps from 3s to 3py, now this becomes what? Partially filled. Understand? Now this is the electronic configuration of aluminum in excited state. Before one was the electronic transition of aluminum in ground state, and this is the electronic configuration in excited state. Now there are 3 half-filled orbitals with the aluminum, 3s, understand, 3px, 3py. Understand? That's why aluminum is forming 3 bonds with chlorine. This is 1 chlorine atom, Cl. This is 2nd chlorine atom, and this is 3rd chlorine atom, Al3. Al3, aluminum trichloride. Understand? Now if I look, there is still 1 more subatomic orbital is vacant, that is 3pz. This is still vacant with us. So this vacant subatomic orbital, that is 3pz, I am showing here with the aluminum atom. This is what different. This is the vacant orbital which is present still with the aluminum atom. Due to this vacant orbital, aluminum trichloride is known as Lewis acid, because this aluminum trichloride has the ability to accept lone pair of electrons. Now what happens? Basically, due to this reason, we are using Lewis acid in this kind of the reactions. Basically, this 1 lone pair of electrons, the aluminum will attract from the chlorine and will accommodate here. Understand? When these lone pair of electrons leaves from or goes from the chlorine atom, there will be a positive charge on this chlorine atom. Now this chlorine atom wants to stabilize itself. How it stabilizes itself? Immediately after leaving this lone pair of electrons from the chlorine atom, now this will trend to stabilize itself by attracting these lone pair of electrons from the adjacent chlorine atom. Now what will happen? What will form basically? This will form AlCl4 minus 1. Why the minus charge comes here? Because this Al basically aluminum make bonds with this chlorine atom, and this chlorine atom attracts the electron from this chlorine atom. That's why here is Cl negative, plus there will be Cl positive. Cl positive. Why this becomes Cl positive? Because this lone pair of electron now has gone from this chlorine atom. This becomes Cl positive, which is known as chlorinium ion, as I told in the process of chlorination. This is our electrophile. This is what does want? This is our electrophile. Now the second important question which I asked in the initial, that why we should use anhydrous Lewis acid. That means a Lewis acid without water molecule. If I use hydrous Lewis acid means the Lewis acid which contains water molecule. That is hydrous doesn't. Now what we know, that there is two lone pairs of electron on the oxygen atom. Now if I use hydrous Lewis acid, the vacant orbital of the aluminum trichloride will attract the electron from this oxygen atom. When the aluminum make bonds with this oxygen atom, then it is useless. Then it can't play any role in the halogenation, because it has filled its vacant orbital by the help of this oxygen atom. Then we are unable to form this chlorinium ion. When there is no chlorinium ion, there is no chlorination. Clear? Shortcut. Understand your student? So that's why we are using anhydrous Lewis acid, the Lewis acid without water molecule. That's why we cannot use hydrous Lewis acid. If there is no hydrous Lewis acid like this, there is no chance to make aluminum a bond with the lone pairs of the oxygen atom. Very simple. Understand? This is the step number 1, which is the generation of electrophile. Now step number 2. Step number 2, which is known as formation of benzenium ion. Formation of benzenium ion. I will remove this one. Understand this one? Formation of benzenium ion, or this is also known as sigma complex, or this is also known as iridium ion. We will again explain all the reason that why step 2 is known as iridium ion, sigma complex, benzenium ion. Understand? Now what happens? This is benzene molecule. This is one of the hydrogen atom. This is Cl positive chlorinium ion. Now the double bond of the benzene will attack on it. This is very simple, because this is a strong electrophile. Now the double bond of the benzene can attack on it. It forms a sigma complex. What does mean by sigma complex? We will explain here. This is Cl, and here come a positive charge. Understand this one? There is positive charge because this carbon attracts the electron from this one and share this electron with this Cl positive. Since this is electron deficient, this electron, the electron to the chlorine atom is basically given from this carbon. That's why here comes a positive charge on this carbon atom. Now this structure is known as benzenium ion. Why it is known as benzenium ion? Because this is a benzene part and now there is a positive charge on this. That's why it is known as benzenium ion. This is also known as a sigma complex. Why it is also known as a sigma complex? Here is a double bond. This is what? A double bond. On the other end, there is no double bond. The double bond is eliminated. Now there is a single bond. We know single bond is also known as sigma bond. Since double bond is converted into sigma bond, plus this is a complex structure, that's why it is known as sigma complex. Understand? This is also known as uranium ion. As we know that arene is the second name of the benzene. Again, there is a positive charge on arene, that is benzene. That's why it is known as uranium ion. Understand, everyone? Now what happened? This is also the resonance stabilize. If I ask which of one is most stable in these two, this is more stable. Here is a conjugation, understand? But here we destroyed one double bond, we decreased the degree of conjugation in this system. But this is also to some extent, it is also stabilized, because this is the resonance stabilized. The process of resonance can occur in this complex. How it can occur? We know that there is a condition for the resonance. If there is double bond, with that double bond there is directly single, with that single there is directly a positive charge, just like here. Then there will be resonance. Understand, everyone? Now this is resonance stabilize. How it is resonance stabilize? This pi bond will shift here. It will form a structure, especially this one. This is hydrogen, this is Cl. Now double bond comes here and the positive charge comes on this carbon atom, because the electron from this carbon is gone or is shifted towards this carbon atom, and this is the double bond. Again, this situation, that is double bond adjacent with single bond, directly adjacent with positive charge. Again, this situation is present in this complex, so there will be resonance. Simply this pi bond will shift here, one more resonating structure will form. Understand, everyone? This is quite easy. HCl double bond. Now positive charge comes here. Now no more is this system is no more present in this complex, because this is double positive charge, this is single bond, again single, single, single. There is no double bond directly attached with this bond. If there was a double bond here or here or here, then there may be conjugation present and one more resonating structure will be formed. But since there is no more this system in this molecule, it stops. More resonating structure will not be formed in this direction. Now this system is present in this side. Again this will shift here, it will form this structure, and this will shift here, it will form this structure. Understand this process? Once this convert to this one and again this convert into this one, this process is continued. This process is only continued when this hydrogen is not eliminated from this part. In step number 3, this hydrogen, or I mean this proton, will eliminate from this part. Here a double bond will form, the molecule will be again stabilized. Understand? So you have to remember these are the resonating structures of these sigma complex. This is a step number 2. What is step number 3? It is very easy. That is elimination. Elimination means removal, elimination of proton. Proton will be lost in the last step. Suppose this is the sigma complex, hydrogen Cl positive. With this sigma complex we will use AlCl4 -1. Why we will use this? Because this is catalyst, this is unstabilized. If I write like this, AlCl3 Cl negative, Understand, student, what will happen? This Cl negative will give its electron to this proton. Proton will give its electron to this carbon. This carbon in turn will give its electron to this carbon. So a stable compounds will be formed. That is chlorobenzene. Again double bond will come here. And that is HCl. HCl plus AlCl3. This is Lewis acid, which came to its original state as it was in the initial. Understand? So how it was? This is chlorobenzene. This is what is not? This is chlorobenzene. So this is the mechanism of the halogenation, which is very easy. Understand, everyone? This is catalyst. That is our catalyst. And this is HCl formed, which is present also here. And this is our chlorobenzene, our main product, which is this one. Understand? This is the mechanism of the halogenation. I hope you have learned the halogenation mechanism today. So inshallah, I will meet with you in the next class.